discussed yesterday, I say that there were two beginnings of quantum mechanics that differ by the way that they look at the vector in Hilbert space. The Schrödinger approach was to take this vector and expand it in complete set of eigenvectors, which are position eigenvectors. So as a function of time, this will be amplitude. They depend on time, and this function is the one that has the Schrödinger wave function, and it behaves like a wave because the Hamiltonian is of the form, if the Hamiltonian is of the form p squared over 2m plus some potential v of x, then because of that thing, it's only second derivative with respect to position. This is time derivative, so this looks like a wave equation when we look at that thing here. So this was very easy to interpret and to understand, and that's why everybody, after Schrödinger wrote this equation, shows that this is the correct way to do quantum mechanics. It has a nice intuition about it because it's a wave. We all know what waves mean, and it's very easy to solve, much easier to solve more complicated problems than the Heisenberg approach. The Heisenberg approach was to look at the vector psi, and instead of expanding it in position representation, Heisenberg looked at all the operators, A, that act on psi, and discussed the time evolution, not by looking at the time evolution of psi, but instead by looking at the time evolution of the observables, and for them we have the Heisenberg equation of motion. And I was claiming that although the Schrödinger representation seems to be much nicer because it's directly connected with what's happening in space, it describes a wave motion that we are all familiar with from classical physics. Nevertheless, there is a big problem in interpreting what it means, because when we have a single particle, and we claim that this single particle is described by a wave in space, there is no way to interpret this amplitude or these values in space, because there is no experiment that should show that they exist. Any experiment that we look at this particle will always find it at one location. It will not find anything that is spread in space. So, although mathematically this looks like a very nice formalism, the physics behind it is not clear, and that is the reason why it was very difficult to develop intuition about what happens in quantum mechanics, because the idea that a single particle can be at the same time at many different locations. People talk about a particle being at the same time at one location, at another location, and there was no way to understand physically what it means, because if the particle has a charge and a mass, being at two different locations doesn't mean that the charge and the mass is in some sense partly here and partly there. But people thought, nevertheless, although it's not clear what it means, that is the only way to explain interference phenomena. Because if you look at the two-slit experiment, we know that if the two slits are open and we send one particle after the other, there will be some positions here, where we record it either in photographic plate or counter. There will be some positions here, for example, where if both slits are open, we never see a particle there. If either one of the slits are open, we see particles there. Then the only way to explain it, people thought that the only way to explain it is to say that something went through here and something went through here, because that's the only way that we knew classically how we can get destructive interference. So although nobody had a real intuition what moves here and what moves there, Because if we look, we always find the particle only one there. So there is no intuition about what moves there, but we say it must be there, because otherwise we can't understand why there is zero there. And then what I want to show you is that this is really not the correct way to think about interference. The correct way to think about interference is to realize there is a fundamental difference between classical dynamics and quantum dynamics. Quantum dynamics, which is the Heisenberg equation of motion, has truly no local features in it, and that allows you to understand that the particle can go here and knows whether the other slit is open or not because of this non-locality in the quantum equations of motion. So I finished last talk by showing that if we look at the Heisenberg description of a particle that is in superposition of 2 points, we find that the Heisenberg operators that are relevant for this situation involve in them this quantity which is cosine of PL over H bar. This is a property, it's a function of the momentum itself, but it's a function really of the modular momentum. Cosinus PL over H bar has the property that if P goes to P plus any integer times H over L, this thing remains the same because you add here multiples of 2 pi. That means that really this function tells us not what the momentum itself is, but only what the modular momentum. If we look at P modulo H over L, that means that if this is the momentum, that we have this function, this periodic function. Each time we change the value of P by P plus H over L, the function comes back to itself. So we find that in the deterministic operators, in the operators that describe the typical situation for two-slit experiment, which are superposition of two such waves, what describes the property of that thing is this quantity P modulo H over L, which is really truly only a quantum property. Because if we go to the limit with H goes to 0 and keep L finite, this will oscillate infinitely fast and we will not be able to measure it. So already in this quantity we see first of all an indication that this is something unique for quantum mechanics, and we see that it must be the correct description. If we look at observables as operators, we look for eigenoperators for this situation, it must involve this function. And I want now to prove to you that indeed this function has non-local equations of motion if we look at the Heisenberg representation. So let's just discuss it. If I look at an Hamiltonian H, which is equal for simplicity in one dimension, px squared over 2m plus some potential v of x, and I look at the quantity cosine, let's look at e to the I p over p0 times 2 pi. I will later discuss this plastic summation conjugate to get an emission operator, in this plastic complex conjugate, to get an emission operator, but let's look at this one itself and ask what is the equation of motion for this quantity if we consider it classically and if we consider the same quantity quantum mechanically. If I look first of all at the time derivative, if I look at the time derivative ddt of e to the I p over p0 classically, so we know that that is the Poisson bracket between e to the I p over p0 and the Hamiltonian. So the Poisson bracket, the derivative of this with respect to p times the derivative of h with respect to x, minus the derivative of this with respect to x, which is 0. So therefore, this is simply ddp of e to the I p over p0 times dv dx. This is the Poisson bracket. Now, ddp of e to the I p over p0 is I over p0 times e to the I p over p0, and dv dx is simply the force, or minus the force. So we see that that quantity, its time derivative, is different from 0 only if the particle is at the location where there is a force. Now let us see what is the equation of motion for the same quantity if we look at the Heisenberg equation of motion. So now we have to calculate e to the I p over p0 commutator with v of x. That will be the thing that will tell the time derivative of this quantity when we do it by Heisenberg equation of motion. So now it's a commutator instead of a Poisson bracket. So for a commutator, we have to calculate e to the I p over p0 v of x minus v of x e to the I p over p0. Now if I write p0 to be equal to h over L, so this is equal to e to the I p L over h bar times v of x minus v of x. There was 2 pi here. So this is e to the I p L over h bar v of x minus v of x e to the I p L over h bar. Now e to the I p L over h bar is a translation operator. So the final result here is v of x plus L minus v of x times e to the I p L over h bar. And now we see something interesting, because we see that the time derivative depends not on the force where the particle is, but it depends on the potential at a distance L away from the particle minus the potential where the particle is. So that begins to show us that there is hope to understand something new, because we say if we have a two-slit with distance L apart, and we claim that when the particle goes out from the two-slit, the important eigen operator involves this momentum modulo, and we see now that the equation of that momentum modulo depends not only at the potential where the particle is. If the particle goes here, it depends also the potential L away from the particle. So then we have hope now. We have a hope to begin to think in a new way about interference by saying that the particle always goes only to one slit, but it knows that the other slit is opened because the particle, while going through one slit, has also another property attached to it, which is this modular momentum. And this property dictates what will happen later in the interference pattern here, as we'll see. And therefore, there is a new way to think about interference without having to be involved with a quantity that is spread in space for the particle, and which we have no intuition what it means. So what I want to do today is to develop the right language to talk about this situation. You will see this right language involves the necessity to think about weak measurements and to think about pre and post selection. And when we combine all this information together, we'll find a really new way to think about quantum mechanics. But I want to show you a possibility of going through all this root by doing only one assumption. We start with saying that we come to quantum mechanics from classical physics with just one assumption. The one assumption is that we have new dynamics, which this new dynamics is a commutator instead of Poisson bracket. When we do that, we find first of all that there are some non-locality. If there is some non-locality, then we run immediately into difficulty. If something is here that can be affected non-locally by something else, we run immediately to a problem with causality. So the only way that we'll save it, as we will see, is the possibility of uncertainties. If that thing that is affected non-locally doesn't have an uncertainty, then we violate causality. So the next step from this non-locality will be to show that it must be followed necessarily by uncertainties. So that is the next step that comes from this first assumption. If we have uncertainties, then we know that we can define two boundary conditions rather than one. In classical physics, if everything is certain, if we know the thing at one time, we know what it does at all times in the future, we cannot put any other boundary condition. But once we introduce the uncertainty, we'll find that we can describe the quantum system at any given time by two boundary conditions, one in the past and one in the future. Once we do this, we find afterwards that in order to find the properties of these two boundaries, we have to introduce new type of measurement that I call weak measurement. There will be new type of results, that will be weak values, and everything is follows just from one assumption. The one assumption is that the dynamics is non-local, and in that sense I say that this will be approach to quantum mechanics that is similarly to the approach to the other evolution of relativity. There we say there is one new assumption, the velocity of light is the same for all observer. Here I say we have just one new assumption, that we have dynamics that is non-local, and all the other properties of quantum mechanics will follow directly from this. You have a question?
You say that in this way we can keep the idea that the particle goes through one slit,
right,
through both.
Mm-hmm.
Can you give some operational meaning of what does it mean that the particle goes through one slit?
Yeah, because once I will show you that once I am allowed to have two boundary conditions, I will have an interference experiment where on one hand, from the future boundary condition, I will know through which slit the particle went, and from the past boundary condition, I will know what the modular variable is, and from these two I could predict all the interference patterns. If you wait till the end of this session, you will see what I'm saying.
Can you repeat what you just now said?
I said that if the question was, how can I say that the particle went through one slit and nevertheless with three interference patterns? I say that I am able to say it because I will have two boundary conditions in time. The boundary condition from the future will show me through which slit the particle went, and the boundary condition from the past will tell me what modular momentum it has, and the combination of the two will give me the full interference pattern. But why don't we wait until the end of this session? All of this will be clear, okay? So, let me describe to you now the idea that started with the work that I've done in the 1960s with Bergman and Leibovitz.
One more question. The question was that you know that the particle...
Why don't you wait till the end of this session? Then ask the question if something will not be clear. There is something that's called now the ABL formalism, which says the following, that if we have a quantum system, we can define for this quantum system two boundary conditions. The boundary condition time t1 says what was the initial state that we prepared the particle with, and then we say that because quantum mechanics has uncertainties in it, if we start with n particles, all of them with the same initial state, we can do another experiment later that will divide this ensemble into sub-ensembles according to the final result. If you want to think of a simple situation, take, for example, the thing that's called cloud chamber. In a cloud chamber, if you have a particle that comes, a quantum particle that comes here, it leaves spots like this until it comes out. And if you repeat this experiment with one particle after the other with the same cloud chamber, you can see at the end that one particle may come this direction, the other may come in this direction, etc. Now, what we do is the following. We take pictures of all these bubbles for each particle, but then we look only at the pictures for those particles that ended up coming in this direction. So we do a pre-selection that all the particles come in the same plane wave, say, but we look at the recording of all these spots only for particles that end up in this direction. So that means that we have pre-selection and post-selection. It's an exclusive experiment. Exclusive, meaning we exclude all the other results. We look only at the results for those experiments that started all in the same initial state and ended up all in going into one counter at the end. Is it clear? This is pre and post selection. So now when we look at quantum particles that each one of them started at state psi1. This is time now. And we only collect those of them that ended up at the state psi2 at the end. This is C1, and this is C2. And now we ask the following question. Suppose in the time in between, this is the past, this is future, now the time in between, we are doing an experiment, and we collect only the results for these experiments for particles that started at this state and the other state, and in the middle give us some given answer. For example, if the thing that we measure in the middle is some observable that is described by an emission operator A, then if this emission operator has complete set of eigenvectors alpha n, such that A times alpha n is equal to the real number alpha n times alpha n, then we can ask the following question. Start with ensemble of particles here. See how many times did we get in the middle a particular answer alpha n, and ending up in the psi2, okay? So how do we calculate the thing? Usually we say the following. We start at the state psi1, we take the time evolution operator from time t1 to the intermediate time t, project it on the particular result, eigenvector for the result that we want to find out. Then we know we got this answer. We start now with alpha 1, alpha n, evolve it in time from the time intermediate time t to the final time t2, multiplied by psi2. That whole thing is an amplitude to start with psi1, in the middle to go through alpha n, and end up at psi2. And if we take the absolute value square of that, it will give us the answer how many times in the whole ensemble we'll start with psi1, get in the middle alpha n, and end up with psi2, right? So the absolute value square of that gives us the question, how many times in this sub-ensemble we get the answer alpha n. By the way, if we sum up all this absolute value square, we will get 1. We will get 1 because we excluded something. So we have to normalize it by divided by the sum of the squares of that quantity. Now, we do the following thing. We do something that looks very trivial. We take this u and bring it here. And we get now u dagger of T2T times psi2 times alpha n u tt1 times psi1. That number is exactly the same as this one, because we simply did a trivial thing. Mathematically, these two things are completely identical, and therefore we are allowed to answer all the questions about the time in between by doing this calculation rather than doing this calculation. Because they give us the same answer, we are allowed to do it. But the difference between the two calculations is very, very important if we try to understand in a new way what's going to happen here. The first calculation says the following. We start with the value psi1, we evolve it in time until the intermediate time. So this is psi1 of t. When we reach here, we replace it by the new result that we got here. So from now on we have the vector alpha n evolving as a function of time from the intermediate time to final time psi2. And then here we continue with a new vector, which will be psi2 of t. This is a conventional picture of saying that we always have just one vector describing the time evolution. And now we find in this calculation, which we have all the right in the world to discuss this picture rather than that one, because it gives us exactly the same prediction, but this picture is very different. What this shows us is the following. We start with psi1 of t, evolution time as psi1 of t. We have reached the time t here, and we take the vector psi2 of t and send it back in time, because u dagger, if u is equal to e to the minus ihc, u dagger is equal to e to the ihc, which is minus ih minus c. So that means that u dagger is a time evolution in the opposite time. It's going from the future to the past. So we take the vector psi2 and send it back in time. In fact, we have to think about this as a cat and this is a bar. We send it back in time. And we find that we can calculate the results of all these possibilities by using psi1 and psi2 on equal footing. Instead of saying that we always have psi1, then alpha is better, further, we say no, we are going to discuss psi1 and psi2 on equal footing and say that in the present, the particle that has been pre-selected in psi1 and post-selected in psi2, the particle in the time in between has both properties on equal importance. And we magically see that this calculation is infinitely simpler than the other calculation. That from this point of view, we should prefer this one to that one, because here, for each different result, we have to do another Schrödinger equation or another evolution. We have to find different differential equations for each alpha that we get here. And if we make another measurement, we'll have another set of infinite number of differential equations. Here, once and for all, we do one differential equation to evolve this, another differential equation, Schrödinger equation, to evolve this backwards, and then from then on, we just have to use vector product, which is much, much simpler, right? So everybody should prefer this picture to the other one, because it's so much simpler mathematically. But we will see in a minute that the real value of that new picture is that it gives us a new insight about quantum mechanics, new kinds of questions that we can ask, and new properties of quantum systems that are pre- and post-selected. Are there any questions about this?
Yeah.
Yes?
What's the relation with quantum theory?
Say it again?
What's the relation with quantum field theory? Because in quantum field theory, what we do is to take an initial state and a final state, and we ask what is compatible with these two boundaries. So
Yeah.
there is always an initial and a final state
Yeah.
in your teaching. So I wonder how much you are importing on the lesson of quantum
Well,
field theory.
you will see that in fluid field theory, many of the calculations are done by using Feynman path integral, and you say, I'm starting with a given state, I end up in another state, then I can ask some perturbation here and find the correlation. This calculation will be similar to this. But what I'm going to follow now, you will see is completely new that nobody is discussing field theory. But there is also one other thing that will come from this way of looking that people don't usually do in field theory, and that is the possibility of doing the following thing. I can say, suppose I start with the state psi1 and end up in the state psi2, and suppose instead I start with the state psi1 prime and end up instead with psi2 prime. Now, this is one possibility, the other possibility. The question is now, can I find now a way to superpose them, to say that I have either this pair or that pair, and superpose them as amplitudes? This is something that usually people don't do, and this is something that becomes very natural in this thing. But anyhow, independent of whether it's done in field theory or not, I'm going now to find completely new kind of aspect of physics, because once I look at this way, I begin to ask questions that nobody asked before, neither in field theory or in relativistic quantum theory. You will see in a minute. So, sorry?
You make the post selection much later, right? Or later. So then you decide in retrospect everything that happens. I mean, I know that it all works, but
I exactly say what I'm saying, exactly what I've done. In this experiment that I described, I send the particles here, make pictures of what happened here, and then see whether it went this way or that way, okay? If it went this way, I collect only those pictures and ask, what are the properties of those pictures for this pre and post selection? That's a well-defined procedure. Okay, but now comes the really interesting new thing. Suppose I look at the simplest quantum system that I know of, which is a spin half particle with Hamiltonian at 0, so everything is constant of motion, and I start with the spin sigma x equal to +1 at the beginning, and I do another measurement and find that sigma y is equal to +1 at the end. This is T1, this is T2. Now, the conventional picture is to say that during the time in between, because the spin was conserved, we have just a particle that lives all the time here with one value, sigma is equal to +1. This is the usual picture. But now we have a new picture that says actually we have two features or two properties of this particle. Because this one is going back in time, we can say that this particle has both properties, sigma x equal to +1 and sigma y equal to +1 at the time in between. If both of them are really there, why not to now take it seriously and say that indeed in the time in between we have both sigma x equal to +1 and sigma y equal to +1. The question is how are we going to check it experimentally? What is the experimental new information about the system if we take it seriously? Now, there are some trivial things we can say. We can say trivially, if we measure sigma x here, we get +1 because it must agree with the beginning. If we measure sigma y here, we know that the probability half to get +1, and probability half to get -1. we just decide to keep only those that give us +1, we throw away the other, but that's trivial. I mean, it's not that really it has sigma y equal to +1. It has both sigma y equal to +1 and sigma y equal -1. We simply throw away those characters from 1 -1. Big deal. There's nothing new, nothing interesting in that. Then I ask myself the question, what happens if I would measure sigma x plus sigma y? Just one experiment. I want to check if this is 1, this 1, perhaps I will get here the value 2, right? If this is 1, this 1, I should get 2. But the minute I looked at this, I said that's stupid, because if I divide it by square root of 2, I cannot get the value square root of 2 here, because this thing is just a spin component in the x plus y direction. It can be 1 or -1 and never square root of 2. So therefore, I took seriously the picture that this is 1 and this is 1, and I realized that I'm led into a wrong conclusion. That picture seems to lead me to some conclusion that is wrong, so maybe we should solve this picture. But I didn't want to give up so easily, so I started to think more seriously what's going on here. And then I realized the following, that if I make a measurement in the time in between of sigma x plus sigma y, when I do this measurement, I necessarily have to put, for example, in Starr-Gell experiment, an inhomogeneous magnetic field in the x plus y direction. This magnetic field immediately starts to process both sigma x and sigma y along this direction. So sigma x is +1 is destroyed immediately, sigma y +1 is destroyed immediately by this experiment. So in the time that the experiment lasts, which is final time, I cannot check that sigma x is equal to +1 and sigma y is equal to +1, because my experiment necessarily destroyed exactly what I'm trying to measure. So then I posed myself the question, maybe I can look for experiments that will interact so weak with the particle that it will not at all affect sigma x and sigma y, because the interaction with the measuring device will be very, very weak. And maybe then there is a hope to see something new. But of course, at first, you may worry, I was worried, that maybe if the experiment will be so weak, I will also not have any information. Because usually you think that information about something in quantum mechanics must give you some disturbance, and maybe when we go to the very weak limit, indeed we will have no disturbance, but we will have also no information. Luckily enough, this is not the case. Let me first give you an inkling why this happens. It turns out that suppose I make an experiment that gives me only epsilon information. Then I know that I have to repeat this experiment 1 over epsilon time in order to get the final information. So I have to repeat this experiment n times, where n is equal to 1 over epsilon. But luckily enough, it turns out that when you have a disturbance that's very weak, I mean information that's very weak at epsilon, the disturbance goes as epsilon squared. And therefore, in this very weak limit, I can then an experiment. If I repeat it n times, I collect information, but the disturbance was n times epsilon squared, and that goes to 0. So there is a very interesting limit in quantum mechanics, which you encounter it, for example, in the Zeno effect. That's another example where something like this happened. Those of you who know about the Zeno effect, if you reduce the disturbance to epsilon squared, the information that you get is still as epsilon. And therefore there is hope. There is hope that we can do experiment. We repeat it many times, we get information from it without disturbing the system at all. And then if I'm right, in those kind of experiment, I will indeed find that sigma x plus sigma y is indeed equal to 2. And now let me prove to you that this is really what's happened. And that opens completely a new approach to quantum systems that are pre- and post-selected, that those systems indeed behave like they have both information, and if you look carefully not to disturb the system, both information live together there, and when we come back eventually from this to the two streets, we'll find that by doing pre- and post-selection, we can arrange that from the initial, from the past information, we have the modular momentum given. From the future information coming back, we have for each particle through which street it went, and then we collect enough information about the interference, and we see now interference for particles that we know through which street each one of them went, and the explanation for that will be the reason why the particle knew also the other street was because it has a property that lives together with the fact that it goes through one street. That property dictates what the information, the interference will be later, and it has non-local equations of motion. That is the goal that I want to reach, but let me go slowly and prove, first of all, the issues that I told you about with measurement, that I can find information without disturbance. No? What is it? Oh, are we making submission now?
At the moment, this session.
No, I have only 1 hour.
45 minutes, right?
I forgot. You know, the week before, I was giving a set of lectures as well, every day 2 hours. So, okay, we'll continue tomorrow, all right?
Yeah.
Okay.